Our next set of speakers will be talking about how we're going to be moving into the future. So I'd like to start off by introducing Dr. Craig Kundrat. He's the director of the Biological and Physical Sciences Division in the Science Mission Directorate at NASA headquarters. He's responsible for providing strategic direction for the BPS division and overseeing planning and execution of its two-pronged mission of pioneering scientific discovery and enabling human space flight exploration. He was previously in NASA's Human Research Program and Microgravity Program. Before entering science management, Craig was an X-ray crystallographer studying structure and function of proteins and ribonucleic acids. Craig?
Thank you, Doug. I want to particularly thank you, Doug, for your leadership this past year as president, and I hope you enjoy the remaining 6 hours of your presidency. And thank you for the opportunity for Thomas and I to talk to the Society today. It's my pleasure now to introduce Dr. Thomas Zurbuchen, who is NASA's Associate Administrator of Science, and in that role is responsible for NASA's science program, including Earth science, heliophysics, planetary science, astrophysics, and his new favorite area, our beloved biological and physical sciences. The Mission Directorate has a total budget of approximately $7 billion a year. With this program and diverse set of leaders, he is helping answer some of humanity's biggest questions. Where did we come from? Are we alone? And how does the universe work? Growing up in Switzerland, Dr. Zurbuchen was a keen observer of the natural world from an early age, and he received a public education with master's and doctorate of physics degrees from the University of Bern. His science and leadership career has focused on solar, heliospheric, and planetary instrumentation and data analysis as a professor at the University of Michigan in Ann Arbor, where he taught space science, aerospace engineering, and innovation-focused classes. He led several University of Michigan innovation initiatives in both education and in research, one of which led to the top-ranked undergraduate entrepreneurship program nationally. He joined NASA as the Associate Administrator for Science in 2016. His honors include induction as a member of the International Academy of Astronautics, a NASA Outstanding Leadership Medal, and the 2018 Heinrich Greinacher Prize from the University of Bern. Dr. Zurbuchen engages people worldwide with NASA's work and the inspiration of science. He can be found on Twitter at Dr._Thomas Z. And right now, he can be found right here on your computer or your phone. It's my pleasure to turn it over now to Dr. Thomas Zurbuchen.
Hey, thanks so much, Craig. Can you hear me okay?
Yes.
All right, great. I'm just so excited to be talking at this conference. You know, this is my first time to talk to this community, and I'm acutely aware that I have a lot to learn about this community. I do so happily and every week by interacting with Craig and his colleagues in our team at NASA. I also started reading some of the papers there. Of course, some of them I knew before, but I'm excited to learn more, especially as it goes into a discipline that I have not worked in, which is biology, and one that, of course, is getting really, really important in many, many different ways, even more so than it has in the past. Before I launch into this, I just want to acknowledge what an important year we have with the anniversary of Space Station, you know, one of humanity's big labs that has, frankly, you know, been successful beyond expectations, especially of the science community. The work that's happening on the inside of the space station, but also on the outside of the space station, represent most of our divisions, and you know, frankly, has been transformative. Though I heard, you know, there was an amazing talk by Jessica Meir. I have to tell you, the moment it's posted, I'm going to be sending an email. I'm going to listen to it because, you know, I've been following for many, many years the work that has happened there, and especially also what Jessica did, but also Christina and many of the other colleagues who have been in the space station. So congrats to the whole community, the ones that build, the ones that fly, and the ones that utilize the space station. So what I would like to do is really kind of talk to you about kind of the broader context of where biological and physical sciences resides now, and talk to you kind of about two things that are of most excitement to me, not because of the other things being less exciting, but because of the fact that they're really on my radar, and kind of are symptomatic of other topics that are there as this community is kind of ramping up to its decadal with important questions that need to be asked and answered in the next decade or so. So the next slide shows one way to organize the science community, and that is by key theme. At the heart of science is discovering the secrets of the universe, whether that is on Earth by understanding the fundamental processes that give rise to melting ice, to transport of pollutants, of processes that are governing our home here, to the deep reaches of the universe, in which many questions are out there that are at the heart of these, processes that, frankly, at this moment in time, we don't know yet. Questions about dark energy, dark matter. Some of these questions, of course, being only decades old, because, of course, they result from observations of unexpected, surprising facts. The same is true with, of course, planetary worlds that are residing out there, and our star and the world in the middle, as well as much of the work that's happening in biological and physical sciences. Discovering the secrets of the universe is one of the most important things we could be doing as humans, even if there was not a single startup immediately coming from that. That alone is what has in many ways changed and affected and directly actually driven not only what we know, but how we think about ourselves as humans. So we think of it as a really critical part. What's amazing about science is that work of underlying science actually does have impact, and it's really, really useful, and it is one of the most important economic triggers. Protecting and improving life on Earth and in space so often comes from actually understanding the secrets of the universe, whether it is by our daily weather forecast, whether it is by disaster relief, whether it is by actually providing the underlying knowledge to live and work in space, just like this division is doing. Protecting and improving life on Earth and in space is our brand, of course, is application motivated fundamental science that is really happening up there. And is absolutely critical, kind of enabling human spaceflight, especially long duration human spaceflight. But the research is a really important goal. And yes, we are excited about companies that are growing as part of that in all those domains. We're excited about being customers of those companies. We're excited about finding modalities that, frankly, we couldn't even have thought about at the beginning of the space station, in which kind of companies and us in the government can lock arms and enable achievements that, frankly, were beyond the reach of any one of our domains separately. One question in the discovering the secrets of the universe element has the word life in it, which is search for life elsewhere. And that is an indication that the astrobiology, which is kind of the one-word version of that sentence, or that, that expression here, is a critical element of so many of our disciplines, whether it is in planetary sciences, whether it is in astrophysics, but also whether it is and really understanding a lot of the kind of the fundamental mechanisms in biology at various levels. Searching for life elsewhere is a fundamental question with huge impact, not only, again, how we think, what we know, and how we think about ourselves, but also, frankly, about kind of domains that it will open kind of over and above, I think, what we can imagine in many different ways. So for us, this is how we think about science, is by its motivation. Another way to think about science is on the next slide, and that is by platform. And if you look at this slide, you see a lot of words. Some of them are bold-faced. Some of them are in normal font, and then there's colors there. The key on the right tells you what they are. The ones in normal font are missions or experiments that are already flying. You see in boldface the ones that are under development. Your eye already caught that at the top left of this chart is astrophysics with its missions like the Hubble, IXP that is getting ready for launch next year. Sophia, other kind of investigations like that you see around the sun, heliophysics, which of course are not just missions of the sun, but also the Earth environment. But then, I want to draw your eye down there by Earth science, planetary science you see there, but you want to draw your eye and kind of look at this kind of band around the Earth, kind of along the orbit of the space station. You see how important the space station has been. This is only a subset of the experiments that are there, and Craig can, of course, talk about each of them in a lot of detail. I'm going to talk about a couple of them. But you see kind of, I think what many people miss is how many disciplines are represented, really looking at the space station as a platform. And I have to tell you, for us, low Earth orbit is a critical part and remains a critical part, and it kind of the, of investigations. And for us, joining our human exploration friends and also commercial explorers that want to go to space, as these platforms become available, is I'm sure something that we'll talk more about as we go forward. But speaking about the space station, let's look at just the next slide, in which we see the operating and future fleet according to this. And you should see the richness from the astrophysics missions called NICER and others to AWE, which is a mission looking at the upper edge of the atmosphere out of Utah State, to many of the investigations that are there, again, from Cold Atom Lab to biological experiments and test beds that are there, all the way to earth science, looking at ozone profiles, as well as, look at ecostress, for example, as well as others that are being developed. For us, Lightning Mapper as well. The space station is an incredible platform for science, again, both on the inside, on the outside. And I want to, again, congratulate the team for 20 years of exciting collaboration. And I want to tell you, kind of the science community, kind of in a broader sense, has been a latecomer to this. It took the science community a long time to learn about this, which is kind of a shame, because there are great ideas out there, and I just hope we learn from this lesson. So kind of as we go with the Artemis program towards the moon, on the surface of the moon, that we don't get our kind of 10 years behind before we finally recognize how important these platforms are. Of course, that's exactly what we're doing right now in our deep collaboration with human exploration, which remains strong even as biological and physical sciences moved to SMD. Our next slide basically tells you what's my highest priority, besides integrating, of course, our colleagues from biological and physical sciences and empowering them and enabling them to use the capabilities that we have to actually run the best program they can. That's what we're about. So you get science, whether it's in your own career or whether it's in our programs, is a very aspirational thing. It's finding that path between the impossible and the irrelevant. Right there is in the middle is breakthrough science. And for me, this what we're using as a tool to find that and help prioritize the many great ideas that are there, the decadal survey that is just starting right now in its activities, we really look forward to. There's elements there, such as research campaigns. What we know is, of course, that the RNA process and some of the, call it $1 million size kind of, steps are really important. And we surely want to continue those, having been dependent on research and analysis as an educator as well as a researcher. I'm a big champion of research and analysis, in a broadest sense, from, taking kind of really high risk shots on goal, high risk, high impact, to really moving, stepwise the state of knowledge forward. I'm a huge champion of that. Research campaigns indicate that not every topic really fits that model, that you need to sometimes topple down. And you know that kind of setting priorities is a really critical element to finding the right kind of stride of moving a field like this forward. Research campaigns, we believe, can enable that kind of critical mass investments, kind of indicating our impatience and excitement at the same time of moving important fields forward that are there. And we think this is really going to be exciting for us to really create these critical size groups and moving them forward. We have key stone capabilities for single venue hardware-based efforts, again, making critical size and investments. And we're, frankly, as we go looking forward at this, we're using best practices from other fields to really say how much will that cost, right? It doesn't help us in the long run to kind of do an enumeration of many, many priorities and not having the ability of moving them forward. We want to, have the same kind of excitement, the same kind of drive, both towards fundamental science and towards applications, as we have in so many of the other disciplines, both in biological and physical sciences. So speaking about that, my next slide introduces transformative science, really driving towards discovery. Remember that kind of discovering the secrets of the universe, and for us, that's in our DNA as researchers. We have that, we know, and there's many different lines of that, but finding the unique place where the only way or the best way to make progress is actually in space is where biological and physical sciences is really just at its best, and that's where we want to move it forward. I want to talk about one example, and that is on the next slide, which is the Cold Atom Lab. What I love about this science discipline, I already talked about Jessica earlier. This is Christina, of course, assisting with hardware upgrades of NASA's Cold Atom Lab in the International Space Station in January 2020. So for me, this is an example, this Cold Atom Lab. How do you know what makes it a great example, right? So first of all, this overall science, both Einstein condensate, the cold structure, of course, are very much, once you drive down at the lowest energy of these atoms, are very much affected by gravity. So of course, if you're really warm and the walls are the critical element of your experiment, that's one part of phase space. The moment you go really, really low and then actually start really looking at multi-body interactions, being cold and being able to kind of reduce gravity and the time scales of gravity, think of it like how long does a particle take to fall through an experimental volume, right? Kind of that time scale, is really making that longer, kind of opens up doors of investigation that are frankly, not achievable at this moment in time, or, in certain cases, never be achievable in its accuracy and kind of in its ability right from Earth. And so what's really cool here is, of course, our astronauts are really critical in this. And I love, always kind of recognizing, of course, that science is an activity of people, of individuals, and how lucky we are that we have astronauts as capable and as important as Christina and others kind of working on this. So let's look at the next slide, which basically shows you kind of how, of course, science works like this. Kind of I have to tell you, in our meeting room, we have a poster of kind of recent title pages of Nature and Science and kind of equivalent, that are out there. So for me, like, we're heading towards the top. Kind of, again, we want to drive forward on this. And, I love this particular title page, kind of, again, because it shows the importance of Cold Atom Lab and also the relation to human exploration that is there. Of course, Cold Atom Lab instrumentation is designed to freeze freeze gas atoms to a mere billionth of a degree above absolute zero, and that's a lot colder, of course, than the depth of space. And really, what we're trying to do is using this as a pathfinder for quantum science in space. Really, its capabilities are best applied to research of few body systems, especially like Eric Cornell's experiments of three-body Efimov states that were, a very exciting state of matter with multiple bosons interacting in unique fashion. Of course, that Russian scientists predicted that in 1970, and the first experimental proof was in 2005 in Grimm's group in Austria, where a lot of this quantum theory, especially entangled states and so forth, kind of in that region of the world, really important work has happened. And I just want to, the reason I'm saying that is just to indicate how important and how recent this is. So basically, these observations of large, long-lived quantum states, also collective states, allow experimental tests of theory that, frankly, are a model for physicists to predict complex systems and find applications in the world. I really, the way I think about it is the cold atom lamp is a gate into the quantum world, kind of for the same way as the James Webb is a gate to the early part of the early history of the universe, which is both kind of the real mysteries and challenges that remain to be discovered, and this is one of those examples. The next slide, of course, tells you in what way we're looking at this in the context of the decadal, and of course, yes, this is an example. I trust that the capable and amazing community listening to this has many more ideas that are out there. Well, which ones are the most important ones to really look at this next generation of kind of experiments that are enabled by this microgravity environment, and also looking at looking at fields across the board. We've also, of course, seen recommendations of space-based research in 2019. AMO and the Plasma 2000, and we really want to see greater detail and again prioritization in the decadal. The most important thing that I want to talk about is a guy who's worked a lot with decadals, both as a vice chair of one of them, worked on 2 decadals personally, but also as a former member of the executive committee of the Academy's participation is absolutely essential, absolutely essential. And I want to speak especially to you who are an early career member of this important community. This is the next 10 years affects you more than many of the others. So let your voice be heard. I want to talk about the second topic, starting with the next slide, which is, of course, application-motivated fundamental research. Again, protecting and improving life on Earth, which is, of course, that creates the foundation for us to kind of really of deep, of living in space for a long time, for longer travel, but also to actually create impact on Earth down here by learnings that we have up there, and account, in some of the formats, of course, our companies, our products, our new approaches that have tremendous scalability. So let's talk about one of them in the next slide. And
one of my favorite areas of research on the International Space Station is looking at the sustainability of future growth systems for plants like harvestable lettuce for future space exploration.
Yeah, so what Jessica is talking about here is, of course, the vegetable reproduction system known as veggie. It's a space garden residing in the space station. Enables the crew to eat produce grown on board. A really important part, of course, not only for sustainability in space, but also really nutritionally valuable food crops, which are so important as a diet, especially over long times, as we learn from both what it does to the body, but also on the psychological side. There's a lot of studies, even here on Earth, right, that green things in a room make the place better. Trust me, that's something I have a lot of kind of anecdotal confirmation from the last 8 months or so. So I really, love that, and the fact that I'll joke around that since Craig and his team are part of our team, we hear research reports that make me hungry. So that's what's happening here with veggies. Let's look at plant habitat 2 on the next slide. Is pre-flight test growing radish, which is it launched to the space station a little over a month ago on October 2nd. I remember that launch. Was outside watching. And primary goals of the Plant Habit 2 investigation are to measure the metabolic and physiological responses to radishes grown in the advanced plant habitat facility. And research reflects NASA's support of the studies that investigate nutritional value, plant performance, and cultivation conditions applicable to plant growth in space and on planetary surfaces. And of course, the ones of most importance and interest to us are the Moon and Mars. So again, just a critical element of our work up there with complex systems, well more complex, I believe, than some of these bosons we just talked about in the Bose-Einstein condensates or others, with multi-dimensional spaces in which they live in terms of processes and characteristics and systems. So looking forward, next slide. There are several areas of complementary research that between the space biology community and astrobiology and planet protection research communities. Now that all of these are part of our science mission director, it's a perfect time to explore how we can work together to broaden our scientific horizons. We are looking for life elsewhere with a sense of urgency we've never have, and since frankly, the early Mars missions, the Viking missions, and we're doing that systematically with many missions on Mars, with observations of ocean worlds, with exoplanet observations of the types we've never had, with learning about the planetary atmospheres and their space weather impact. In that puzzle are important contributors that are to this most challenging proof, frankly, in space history, proving that there's life elsewhere, and the proof that that experiment was not significantly affected by life on Earth. This, of course, relates to both diagnostic techniques, but also how to handle a clean spacecraft. These topics have to interrelate for all of us who have done experiments that, with tough signal to noise conditions. It's important to know what the noise conditions are. So how do these life forms that are inadvertently as part of our kind of conditions and kind of left residuals of those on our spacecraft, to a certain degree, how do they kind of affect and these experiments, how do they survive in space travel, what do they do? And so that kind of work is just so critical, I believe, and again, urgent as we go forward, as part of the robotic exploration piece, but also to enable safe and human, sustainable human exploration. So I just urge you all to use meetings such as this, to discover the commonalities within the communities and expand on areas of mutual interest, and participate in the activities that are led by Craig and his team together with our colleagues of the ASGSR, on really getting ready for that decadal. Yes, voice your opinion, put your white papers in, and participate in these town halls. And with that, I'll get to the next slide and indicate that from my part, Craig, I'm ready for questions. There may be something you want to add at this moment in time, Craig.
Thank you, Thomas. I think the way we're working this is I'll give my talk and then we'll take questions at the end. Do you have time for that, Thomas, or do you need to take questions?
Oh, I'm standing by. I'm turning it to you and I'm going into the background. Go ahead.
Okay. All right. Well, thank you very much, Thomas, for an outstanding talk. I think that is a beautiful introduction to the Science Mission Directorate and some great examples of how biological and physical sciences integrates in quite seamlessly into the SMD goals and manners of doing science. So I'd like to use this talk as a bridge between Thomas's introduction to SMD and BPS and SMD and to the sessions that we'll have at the top of the hour. So we have parallel sessions for space biology and for physical sciences that will go into a lot more detail about the content of those programs. And so what I'd like to do now is provide a bridge with two pillars to it. One is the move itself to SMD to bring the community up to date. And the second is to expand a bit on the decadal survey effort that's about to launch. Next slide, please. So first, the mechanics of the move. So in July, Biological and Physical Sciences Division was created in SMD. After being in the Human Exploration and Operations Mission Directorate for about a decade, This is the first time for a long time that space biology and physical sciences has been with the other science disciplines. We moved space biology and physical sciences en masse, that is, intact. So all the programs, projects, and grants moved intact. All the personnel moved. Our organizational structure within the division and our relationship to the field centers, all intact. One difference is when we were in HEO, the Human Research Program, which is run by Bill Pulaski at Johnson Space Center, was mapped to our division. We had an oversight and advocacy role. The Human Research Program remains in HEO, but is now in the Human Spaceflight Capabilities Division under Benji Newman. So we still, as I'll say later, we still have very close ties to HRP, but organizationally, HRP remains in HEO, whereas we are in SMD. So that's the structure. In terms of function, if we go to the next slide, we start out with a great deal of continuity. BPS retains its two-pronged mission. We're still about pioneering scientific discovery and enabling exploration. The major engine driving the scientific discovery is the decadal survey, which we have from 2011 and are about to begin the next. And enabling exploration is driven primarily by NASA's exploration needs. We're also maintaining our partnerships. So within NASA, we still have the same close relationships with the Human Research Program, the Space Station Program, CASIS and National Lab. In fact, we're actually developing a much closer relationship with CASIS and National Lab. Still have our relationships with the Advanced Exploration Systems Division within HEO and the Space Technology Mission Directorate. We're still working closely with other government agencies like NIH and NSF and many others. And of course, our international partners as well. The intent is in year one, so we joined SMD in July. So until next summer, the major emphasis in year one is for BPS and the remainder of SMD to get to know each other scientifically in terms of content, but also our processes and the way we work. And also get to know our research communities as well, because there are substantial sociological differences in our communities. Having said that, there are some changes that we're easing into, some process changes. And for our research community, I think the first example of this that you'll see is in our research announcements. So at the beginning of September, we released a research announcement for physical sciences in our usual NRA mode. But soon you will be seeing our announcements come out under ROSES. That's an SND umbrella call, much like the PSI umbrella call in physical sciences or the space biology Ross Bio. But in SMD, ROSES, which stands for Research Opportunities in Space and Earth Science, is a very large umbrella. And we will be a couple of spokes in that umbrella coming soon. After next summer, we can expect, having gotten to know each other, more substantial and strategic changes. I don't expect any step functions, but you might see some new vectors. But it's too early to say, what those will be, because we're still in the get to know one another mode. Having said that, it was apparent from the very beginning, in fact, before we even made the move, there are several opportunities available as we move into SMD for us as a division and the community. So first, as Thomas alluded to, there's a lot of touch points within the other SMD divisions for coordination and collaboration. So for example, in astrobiology and planetary protection research, which are within the Planetary Sciences Division, space biology's microbiology effort is in an outstanding position to interface on the one hand with human exploration, where you have a space vehicle where you have microbiomes associated with the crew, with the plants, and with the built environment. And then you have the interaction with the environment, and with Mars in mind in particular, the forward contamination that will take place. There is no way we can design hermetically sealed exploration systems. So our Earth-based biology is going to escape into the Martian environment, and that triggers planetary protection concerns. And so our microbiology program interfaces nicely with questions that planetary research has, and also questions in astrobiology, which concern how life can adapt to new environments and what kind of shocks it can tolerate and how it evolves over the long term. Similarly, in the astrophysics division, we share common research questions like dark matter, dark energy, Einstein equivalence principle. Now we share the questions in common. The platforms that are used are rather different in scale. Our colleagues in astrophysics tend to use things like galaxies and the universe as their object of study, whereas we're using things like Bose-Einstein condensate at a much larger scale, on a millimeter scale tops. Nonetheless, there are interesting areas where we might have coordinated efforts to tackle some of these fundamental questions about things like dark energy. There's also other areas like dusty plasmas, where we do experimental work on station, and that's another area of astrophysics interest. So those are just some of examples of touch points that we have with other SMD divisions. There's also learning about best practices. So for example, in heliophysics, they have a program called DRIVE, which is an interagency effort, primarily with NSF, but I believe it involves some other agencies as well, that works at coordinating effort at both the theoretical and experimental levels to advance an area of research. So we look forward to learning more about that and how we might enfold that into our partnerships. And then lastly, as Thomas emphasized, SMD is very keen on transformative research. And the decadal survey is, as he said, comes at an outstanding time as we make this move into SMD and are charting the future of biological and physical sciences. We can really start thinking much more about how we can use the spaceflight environment for truly transformative work. All right, let's take a little digression for a moment. What do we mean by transformative research? Next slide, please. This can mean different things to different people. If you've had the philosophy, if you've taken a course in philosophy of science and read The Structure of Scientific Revolutions, you'll recognize this. This is from the NSF, and basically transformative science is either a change in paradigm for a field or opening up a whole new line of investigation, a whole new field. So it can involve new ideas, discoveries, or tools, and they radically change our understanding of something that we thought we understood, or maybe it's an open question that we didn't have an answer to. It could also impact engineering concepts. So getting back to our two-pronged mission, we are looking for transformative work in pioneering scientific discovery, but also enabling exploration. Breakthroughs on either front are what we seek. And in many cases, it can be a breakthrough on both, where the fundamental science undergirds practical applications. It can also be radical change in educational practice, and transformative work leads to the creation of either a new paradigm or a new field of science, engineering, or education. So again, in short, it's either a new paradigm or a new line of research. Now, the decadal survey is, next slide, please, is an outstanding vehicle for really focusing thought on the potential areas for transformative research. How can we use the spaceflight environments that we have access to and will have access to do work that cannot be done on the ground, and therefore has a much higher probability of changing a paradigm or opening up a new line of research. So for those that don't know, that may not be familiar with decadal surveys, they're created by the National Academy of Science and Engineering and Medicine. They are very large efforts that involve the whole community. They chart out specific recommendations for the next decade of research, but they also are really laying the foundation for the decades that follow. So they have very large and long-term impact. Our current decadal survey has a statement of task. There's a URL listed here that you can go look up to look at the details. And we're about to enter negotiations with the national academies on the actual execution of the decadal survey effort. And that should start either late this year or very early next year. Now, the decadal survey process is not the academies closing the doors and having deliberations in smoke-filled rooms. It is very much a community-driven process where they want maximum participation from the research community at all career stages, nationally and internationally. And the major vehicle for transmitting these ideas to the decadal survey effort are white papers. And I am very pleased to say that ASGSR leadership has really embraced this opportunity and is putting on a series of town halls to start with that will look rather broadly at various areas of research, and then follow up those town halls with more focused meetings to really dig into what white papers might be generated by the community and who the champions might be in the writing, et cetera. But these are very broad tent activities, and I really encourage you to look at the ASGSR website that lays out the detailed schedule of town halls that are occurring this month and next, and we'll set the stage for more detailed meetings coming in January or February. Next slide, please. This forthcoming decadal will be a bit different than the one that we currently use, the one that was produced in 2011. One area that will be in common are research areas as we find in the current decadal. But as Thomas alluded to, there will be a couple of new elements that we're asking for in this decadal. One is keystone capabilities. So these are, relatively speaking, large missions focused on hardware. They're not at the scale of like flagships and SMD, but they're kind of conceptually analogous to that. It's hardware centric because the hardware is really opening up a whole capability to serve a field. And it needs a major investment in the hardware to make that work. So examples that we have in the current portfolio that serve as kind of a guide are the cold atom lab, the combustion rack, and the fluids rack. So this hardware-centric approach tends to be quite common in the physical sciences, where there are large capabilities that are serving multiple investigations. In space biology, just as an aside, we tend to have smaller hardware platforms that are also serving multiple investigations and a community, but generally not at the scale of like a whole rack like we've seen in physical sciences. However, this might be the time for the space biology community to identify larger facilities that would really enable transformative research. So these keystone capabilities are hardware-centric, they support multiple investigations, and typically they're in a single environment, like the ISS and LEO. A second new component are research campaigns. So whereas we have research areas in the current decadal, a research campaign is an extension of a research idea or research area where you have multiple lines of investigation coming together to tackle a transformative goal. It's not focused on a particular bit of hardware or a single environment. It's really a much broader campaign. It could involve ground research, suborbital, LEO, and lunar research, for example. And it's all focused on bringing these threads together to attack a clear transformative goal. So those are two types of content that will be new in the next decadal. There's another element layered on top of these, and that is cost estimates. So we don't have cost estimates in the current decadal, and that becomes a little bit of a problem for us who are implementing the decadal survey, because there is a question of what scale these activities should take place at. So we're looking in the next decadal for cost estimates so we know what range of activity is appropriate for the challenge that we are confronting. Unlike some of the other SMD divisions and some of their missions where it's there's a large history, a long history and pedigree of developing instruments, for example, on spacecraft. In our BPS world, I think there's a much broader range of hardware, and we don't have as detailed a pedigree. And so I think in many of these areas, we won't expect a really detailed estimate. It's going to be more of a range. And if you look at the other SMD decadals, you actually, for some topic areas, you actually see a range that may vary over a factor of 2 or 3. So this doesn't have to be an ultra sharp pencil exercise in these white papers, but having a good estimate within a factor of 50% is going to be very valuable. So the decadal survey is coming at an outstanding time for us because it's in our move to SMD and the focus on transformative research. The decadal survey is really the way to capture the most promising areas for the future in these lines. So last slide, please. To conclude this transition between Thomas's introduction to SMD and the talks we have at the top of the hour, space biology and physical science has moved en masse in July into SMD. Our mission is intact as we're still pioneering scientific discovery and enabling exploration. We have a brand new suite of opportunities to collaborate with our SMD colleagues that we're pursuing, and this decadal survey is about to launch. And again, I really encourage your participation in the process and point you particularly to the town hall meetings that ASGSR is sponsoring later this month and next. And I hope you all become as excited as we are about taking advantage of these changes and capitalizing on them to expand the boundaries of scientific knowledge for the benefits of life on Earth and exploration. Thank you. And with that, Doug, we'll turn it over to you to lead in the questions and answers.
Thank you, Craig and Thomas. That was a fantastic overview of our joining into a new directorate. So we have a couple of questions here. And a question inspired by David Smith on biological community. There are unique facilities and platforms available, for example, on the South Pole, but these require NSF approval and cooperation. Besides the decadal, what else can we do to advocate for improved cross-agency support?
Why don't I get started on this? Yes, we have important work that's happening at the South Pole in a variety of disciplines, frankly. That includes astrophysics, for example. It includes some planetary science, and it does include some of the capabilities that are being there, right? For me, it's actually interesting. I've actually kind of asked my deputy for research to kind of look into this a little bit more. You know, of course, that during this year that we're going through, this program has been massively impacted in a negative sense, of course. The National Science Foundation has decided to not, basically run the program at the size that it was initially intended to during COVID. And I think what's really important, the most important ingredient, especially for those kind of capabilities, is to anchor them in the decadal, because that gives them more importance in many ways. But no matter what, you should know that we are working with our National Science Foundation colleagues, and you should let Craig know if there's specific issues that we're not aware of, that we can make part of this discussion that is happening at the SMD level. So we found really positive interaction with the National Science Foundation as well as other agencies.
Thank you. Kind of an aside issue related to that is a question from Paul Todd on how can we involve our partners that we've had from international collaborations into the decadal survey deliberations.
It is true that the decadal is a U.S. process. There are similar equivalent processes in Europe, similar in Japan, and in other countries and other organizations. Planning activities that have again similar purpose, which is to prioritize given some research relative to each other, relative or their urgency or the stage in that development arc that Craig talked about. And so I think what we have done always, and in many cases, we actually are very openly communicated with our international community, and we're kind of getting into discussions. Even though this is centered on the United States because of the fact that, of course, the taxpayers that are paying for that are in fact U.S. taxpayers, right? Appropriately, it should be anchored here with the stakeholders that are the best stakeholders here, such as the national academies. But that does not mean that we want to exclude the internationals. In fact, if you looked at the planetary, looked at the Space Studies Board, but also looked at other decadals, you will see that at various places, kind of international voices are directly included in that. And so my recommendation would be for this community and, Craig and others, to really keep open the communication with the national academies, especially the Space Studies Board, to look for opportunities like that where that is a critical enabling piece, right? So again, 2/3 of all of our missions in science have international contributors, and because science is such an international activity, we think that's a natural state, and it's something that, frankly, is also reflected in our policies, even all the way to Artemis. International and commercial participation and partnerships are really critical for that. So the same is true here.
Yeah, can I just expand on that? So thanks, Paul, for that question. Sorry we can't have coffee together today in this virtual world. But the statement of task for our decadal, includes a involvement of international partners and awareness of their programs and how we can work together. And we will be bringing that forward at our working level, so to speak, in December when we have our 59th meeting of the International Space Life Sciences Working Group. Later this month, I think it's on the 18th, we have our International Microgravity Strategic Planning Group meeting. So through these venues, we'll be alerting our colleagues that we interact with normally about this upcoming decadal process. So we very much expect a vigorous inclusion of their capabilities. And similarly, the commercial world is another thing that's changed the landscape, and I think they'll be involved a great deal in the decadal survey as well.
Yeah, if you could just expound for just maybe 30 seconds there, Craig, because that's about all the time we have on how to address what you just said, the challenges associated with connecting industry and academia to avoid the dreaded TRL valley of death.
Oh, I get a whole 30 seconds? Well, thanks. I only need 15.
I know. Speak quick.
Right. So that's especially in an evolving market like LEO, I think that is I'll just say it's a high challenge. And I'll say I'm optimistic because we are working more closely than ever with CASIS National Lab, which interacts greatly there. We're working on joint roadmaps. That is going to be one way in which to try and stitch together, at least in the near term, tactical. When it comes to long-term strategic, that may require a different kind of activity.
We have 2 seconds to go. Perfect. So I want to thank our speakers, and we are now going to be taking a break. We will be starting out again at 11 o'clock with the breakout sessions. Oops, that's right now, isn't it? So let's move on.
Thank you.